Alright, everybody. So it's the 19th century. Chebyshev, Markov, and Stilches are playing with continued fractions, and all of a sudden, a new theory was developed. So, in the 19th century, Chebyshev was studying continued fractions, and he noticed a special type of polynomials which he called orthogonal polynomials. These polynomials were later discovered to have numerous applications in different areas of mathematics, including numerical analysis, probability theory, number theory, to name a few. So, um, I guess in honor of Chebyshev, it's best to open up this course on orthogonal polynomials by briefly discussing what Chebyshev polynomials are, which are just a specific type of orthogonal polynomials. But before we do that, let me just tell you what's the plan for this course. Well, I'm planning to cover what's so-called classical orthogonal polynomials, or the classical orthogonal polynomials, such as Hermite polynomials and the class of Jacobi polynomials, and so on and so on. I'm planning also to cover the famous recursive formulas defining orthogonal polynomials. And as we go, we're gonna survey some nice properties of orthogonal polynomials, such as their matrix representation, and so on and so on. And at some point in this course, we're gonna turn to discuss the intersection between the theory of continued fractions and the theory of orthogonal polynomials, and how these two theories, we're going to discuss the interplay between these two theories, and we're going to see how beautiful that is. So I guess stay tuned for that. But for now, for this video, let us discuss briefly the basic definition of orthogonality, and I guess motivate this by discussing what Chebyshev polynomials are. However, we're gonna turn to study these at a more deeper level, but for now, let's just get the main idea of what's happening here. So the story began with the trigonometric identity shown boxed in the screen in front of you, and this trig identity is just like a basic complex analysis thing to observe, or you can use basic calculus to get this. But I'd like to write this in terms of, or to justify this quickly in terms of complex analysis. So here's how I justify this quickly. So what you can do is you can look at e to the I brackets m plus n theta plus e to the I m minus n theta, and you can take the e to the m theta as a common thing, and you're left with e to the I n theta plus e to the minus I n theta. And now by definition of the cosine, this is going to give you 2 e to the I m theta cosine n theta. And if you take real parts, both sides, you will end up with, I guess we need real parts everywhere. So if you take real parts everywhere, over here you will end up with the right hand side. You will end up with this thing. And over here, you will end up with the right hand side. So this will be the right hand side. So this is a quick way of saying why this trig identity is true for every m and n. So Chebyshev made this nice and quick observation. It's also quite trivial to observe that if I integrate now, if I integrate between 0 and pi, I will always get 0. And the reason is, if you integrate cosine k theta between 0 and pi d theta, for every k that is not 0, for every integer k that is not 0, what we have is that this thing is just min k theta over k between 0 and pi and this is always 0 because sine of k pi is always 0. And like this automatically gives you that the integral of this is 0 and the integral of this is 0, and hence the integral of this is 0. So whenever m is not equal to n, and just to be careful here, whenever m and n are both non-negative, just to make sure that this is also non-zero, then whenever like these two integers or these two natural numbers are different, we have this property that it seems like it came out of nothing. It's just a free lunch thing. And there's something pretty deep happening behind this integral, which is like there is a class of orthogonal polynomials hidden behind this integral. And to see this, I haven't defined what orthogonality is, but stick with me. But stick with me while we motivate it. Well, if we take x to be cosine theta, then what happens is we have that theta is arc cosine x, and this thing is gonna be I guess cosine m times arc cosine x, and you can do the same for the second cosine, and this thing by definition of derivative of arc sine is gonna be dx over square root of 1 minus x squared. So if you just take derivative here, you have this dx. Now, interestingly, these things over here are polynomials. So just to clean things up, let's call these the Tn polynomials. So what we're gonna do is we're gonna define the Tn as a function to be cosine n times arc cosine x, and what we end up with, this star literally translates to the integral between 0 and pi of Tnx times Tm, or maybe Tm times Tnx times dx over square root of 1 minus x squared is 0 whenever m is not equal to n, and of course we're speaking of mn bigger than or equal to 0. And excuse me, these boundaries should be updated. This is minus 1, 1. Now, you might ask the question, why are these polynomials? And we're gonna discuss these in more details in coming videos, but just so you see what's happening, t0 is just 1 because t0 is cosine of 0, which is 1. t1 is just cosine of arc cosine of x, so that is x. t2, it's gonna be cosine n theta, so it's gonna be cosine 2 theta, and this is the same as 2 cosine theta minus 1, of course squared, and cosine theta is just x, so this is 2x squared minus 1. And what happens is you can do a basic induction argument to get that Tn is a polynomial for every n. Now, I guess by now this should be surprising enough that out of this, like using this basic trig identity, we got these polynomials that and at the first glance they look so weird, and they don't even look polynomials, right? They just look so weird, and they satisfy this famous integral property. And this definition over here, this shaded definition, is just a specific definition of orthogonality, or just an instance of orthogonality. Though this looks a bit surprising and extremely beautiful, it's kind of not very surprising, because remember, we know that if we look at the set 1 cosine theta, cosine 2 theta, ... we already know that this is a linearly independent set. And thus, we kind of expect a similar. I mean, we just did a basic change of variable, so we expect not to violate this nice property of the cosine space, right? So from now on, we're gonna call t0, t1, t2, dot dot dot. We're gonna call them the Chebyshev polynomials. We're gonna call them the classical Chebyshev polynomials, and these are, and this is an example of an orthogonal sequence. Okay, cool. And believe it or not, these polynomials are like extremely important, especially in approximation theory, because the roots of these polynomials, which are called Chebyshev nodes, by the way, they're just very important in interpolation theory. I'm saying some technical words here, but believe me for now that these polynomials, which are like derived from this basic trig identity, are like just extremely important. Okay, and now what we're gonna do, we're gonna leave this here for now. We're not gonna dig deeper into this. We're gonna leave it here for now, and we're gonna generalize the definition and finish this video there. And then we're gonna see more properties and examples in the coming videos. But before I do that, let me just make a note that the word t for the polynomials, you might be wondering why didn't we name it p or something. The word t, the letter t here is because like a Chebyshev name can be like, for example, in French it becomes like this. So in German it also begins with t. So in honor of Chebyshev, we're gonna call it tn. Anyways, so let me just generalize the definition of orthogonality, and then we're gonna leave it off here, and then we pick up from where we left off in the coming video. So just to make an analogy with what we were discussing with for Chebyshev polynomials. So for Chebyshev polynomials, we have this property that we want these things to satisfy, these polynomials to satisfy this property for every m not equal to n, of course, non-negative m and n. And what we see is, we see like there's an additional function here that is sitting right here, and this function we're gonna call the weight function. So if we want to generalize this notion, what we're gonna do is we're gonna introduce a function, we're gonna call it the weight function, and we want this function to be integrable in the sense that we want the integral to exist and we want it to be finite. And like we want this function not to be zero everywhere, because if it's zero everywhere, then this definition doesn't make sense, because any two polynomials will satisfy this, right? It's always zero. So we want this function not to be zero everywhere, but that's not enough. We want it not to be zero on a set of positive Lebesgue measure. And if you don't know what that is, just think of it as a function whose integral is positive and whose moments are finite. So we want all the moments to be finite, like this. So generally, this is what we require from the weight function to satisfy. So if you have such a function, then we can speak of what's so-called orthogonal polynomials with respect to this weight function, provided they exist. And we're gonna say that a sequence of polynomials is orthogonal with respect to the weight function omega and the interval AB, we're gonna say that this sequence of polynomials is orthogonal if they satisfy the property that whenever m is not equal to n, the integration across this measure or across the weight function is equal to 0 whenever m is not equal to n, and of course here our m and n are non-negative. Notice our weight function in the case of Chebyshev polynomials is the function 1 over square root of 1 minus x squared, and I'll leave it to you to see that it does satisfy the properties that we wanted from the function to satisfy, and the pn's are just the tn's. Now, where I'll have to leave it. I'll have to leave it here, but and then we're gonna discuss more deeper things in later videos. But before we end this video, I guess, let me say a few things about these polynomials. These polynomials, like the moment you have an orthogonal sequence of polynomials, these polynomials are gonna form bases for the space of polynomials, and then we're gonna see how to prove this. This is an easy thing to prove, I mean their roots generally have, like their zeros generally have very interesting properties that we're gonna talk about. And of course, starting with a weight function, we want to see if like orthogonal polynomials exist at all, and this is gonna be the topic of the coming videos. So there's a lot to come, but I wanted this to be a light introduction. So I hope it was motivating enough, and stay tuned for more.